Actually. Okay, everyone, and today I want to talk about a side project that I've started about since summer. Natalia and I was collecting the data for this project, and then I started its analysis. It's been nearly 3 months, and it's around. The title was initiated with this deep learning and ro-vibrational spectroscopy to quantify the constitutions of amino acid mixtures. But I'm getting familiar with the way the research is going, and things might change because it's a trial and error. You try things and maybe it's not favorable. I'm doing this work just for the purpose of publication, but I've learned a lot from this. So it started with this poster that I presented on September 24th, besides our athlete poster. And the purpose is to just compare. Let's go to the next slide. So there's a couple of objectives that I test. I've already made 200 slides on this, but I'm not going to present all of them. Just very quickly, the results and things that I've learned, I'm going to share with you. Maybe it comes of benefit to you as well. But the objective was about comparing IR and ROMR in general, from a processing point of view. What's the difference in pre-processing, and analyzing what's the difficulties and how can we confront with. But apart from that, when we were preparing these mixtures, one dimension was homogeneity and homogeneity effect, but we did a great job in all the mixtures we have prepared, and all of them seem to be homogeneous like each other. So what I ended up doing, just combine all the data together to make a bigger data set. And also I've done the other dimension is to generally compare some deep learning models like CNN versus PLSR, which is the classic method to analyze data or any other vibrational data, mostly in our field. And also I came across lots of literature reviewing. Most of them were quite new, novel, and interesting, that grabbed my attention, that I just want to introduce the idea, but I haven't gone through that much because it was quite irrelevant. And also the whole goal is to generate a robust and effective method, starting from pre-processing both IR and ROMR, and go ahead to different modeling approaches and different cross-validation methods, whether it's test-train cross-validation or it's the coupled cross-validation, and how it affects the results. So the way we started this project was preparing 48 different mixtures of 6 varying amino acids. And the reason why we picked amino acids, these are carbonaceous compounds of soils. And since we are interested in a bottom-up approach of making synthetic soils, it was a very interesting and not very, unknown compound to start with. That's why we started with these amino acid mixtures, but they might have other beneficial from biological point of view and other things that we can just mention in our introduction. And again, here very briefly, this is the things that I've done just for the poster, but everything actually has begun after that. And it's a pre-processing. It's a must do when you start processing up ROMR data. You first do normalization, and the most common one is L2 or Z-score normalization. And then there's background removal that I took advantage of DWT. It's an iterative discrete Bailey transform. And for dimensionality reduction, also I've used DWT. I have the slides on them, which I can go over them separately, but the goal here to just mention everything very briefly, but I have the detailed information and the results from each of them. And then there's a comparison between PLSR and CNN, specifically because due to a paper in 2017, they were the first group that they introduced CNN for Raman analysis, and they've shown that when you apply CNN, you don't need to do any kind of preprocessing except for normalization, which is a must step. And you get nearly the same results. That I also received the same thing, which is quite interesting. And it also has other powers when it comes to fluorescence and noise. And there is other normalization method and the steps to compare which one is the optimal method. And for the homogeneity and heterogeneity effect, so we prepared these samples. We just did the hand mix of the mixtures for A series. For AA series, we did hand mix and perturb to just see a new surface how it affects. And the third one is the mechanically mixed using this magnetic stirrer, but it ended up having nearly the same results. So we just combined all the data to 4,800 Raman spectra of these 48 mixtures. And this is the nature of Raman. I'm sure all of you are more familiar than me that always in spectroscopic data, we deal with high frequency noise and low frequency background. And there is this medium frequency spectra that are of our interest. And there's a correlation between these medium frequency spectra and what models needs to learn for the prediction or classification that we apply. These are some results for the poster, but things have changed. I just show these, and these are different background subtraction. So the way that DWT works is based on the number of coefficients of the frequencies. So we have coefficients for high frequency down to low frequency, and depending on which frequency you are interested to keep and which one to just remove, you can keep the medium frequency for example, the middle picture to just get rid of the background and also get rid of noise. But I started here, so it's actually 4,300 Raman spectra, and depending on the spectrometer camera, the number of pixels or features depending on that. So for conventional research, we have 1024 features. So it means we have 1024 features to define each Raman spectra, and the goal here to make the correlation map from these 1024 features of these 48 different spectra to their pure ratio of amino acid compounds. For example, each mixture is combined of 6 different amino acids, and the goal is to map this Raman spectra to exactly to the 6 different ratio of pure amino acid compounds. And we've collected 30 spectra of each compound to generate these. And as I said, we had 3 different sets in general. This is the correlation map that defines what's the correlation between the different features, where the correlation is highest and where is the lowest. But here it begins to test different things when you collect a bunch of Raman spectra, and your goal is to predict the ratios or classify based on the Raman spectra you've collected. So the first is the averaging effect. When you have lots of Raman spectra, obviously the averaging has a dominant effect and it improves everything very well. Even though it's always said that the more the data, the better for example, deep learning models. But when you have replicas, it's better to average your data before you train on, because it represents better results. And then Among dimensionality reduction and background removal, so for the dimensionality reduction, PLS is a partial least square. It's a least square model, and it's limited to that the number of features should be lower than the number of samples. So when we apply dimensionality reduction, it improves. Why I don't have? Oh, I had some percentages in the bottom. I don't know how to get rid of this line. I don't know.
Also, can you explain what these plots are? I don't really know.
Yeah, sure. I had some percentages here. Don't know how to get rid of it. I'm afraid if I. Yeah, so these plots are 6 different plots, and each one is a calibration between predicted. I should have had one larger. Each of these graphs, like each one is the predicted versus the grand truth or actual amino acid ratio. Since I had 6 different compounds, we have 6 different associated to each different pure compound. Yeah, I should have one larger, definitely. Yeah, and the best overall model is the one that can predict for each compound, can generate a good prediction results for all of them. And the first row is the total, the model that predicts everything altogether. And after that, after each name, you can see the prediction associated to each compound. Like this model, how well it could predict the aniline, predicted aniline versus actual aniline, and toward the end. So this is the definition of these. You cannot see here, unfortunately, but on my screen there is a 2.22% improvement for PLSR when you apply dimensionality reduction. So this is the previous slide. Sorry about this. This is these lines fault that you cannot see the percentage. So for PLSR, if you apply background removal, you get around 8% improvement, while the background removal for CNN model just improves about 1% here. So this is again confirm what I've learned from that paper, that if you use a more sophisticated model like CNN that has all of these neurons and can learn by itself, then you don't need to get rid of unnecessary information, and it learns how to get rid of them itself. And the next slide is the effect of both dimensionality reduction and background removal. That for PLSR, I get about 2.22% improvement, and for the CNN, when I reduce the features from 1024 to 274, the model just ruined. I need to tune this model again to get a comparable result, but the other things came along and I couldn't finish this. But it does a pretty much well job on all the features altogether. CNN doesn't have a big problem with that. Here I want to, so since so far everything was quite well and there wasn't nothing challenging, I start adding dimensions and challenges to my analysis. The first one is the noise effect. So I calculated a signal to noise ratio by dividing the max of each spectra by the standard deviation of the lowest region, as we consider it as noise. And by that, I generated a signal to noise ratio, and then I wrote a noise generator function that can that its amplitude or its coefficient is 1 divided by SNR. It's the amount of noise. The higher the SNR, the lower the noise, and vice versa. So I defined this noise and I added to the Raman spectra. For the first two, which is the amount of noise is too little, and it shows that since noise can add some variability to the data you have, it helps model to learn things better. But as I increase the amount of noise, for example, toward the end, it's non-normalized spectra. When you normalize it, even though it's noisy, but still you have a very good broad features still. So when I add this amount of noise, which is SNR 0.1, PLSR results degrade from about 97, 98 to 78. CNN, I fine-tuned this model to find the best configuration that results the best results. It's 86, and there is an autoencoder. That autoencoder originally is been introduced just for denoising and images and denoising images. So I said maybe I can apply it on a 1D image like this. The result is still undergoing, but the hope I had was that to get better results from autoencoder. It means first apply an autoencoder to denoise the Raman spectra, and then apply a second prediction model like CNN to predict the ratios and get a better results from there. But it's ongoing, and since it's 1D, a little bit challenging than 2D. Yeah, these are some of the results. For example, when I don't normalize the input and it's just noisy, the prediction is not good, and also it's not generalized because I haven't normalized the data. I should, for almost all deep learning models, you should normalize the data, and it's still undergoing. And then here IR data, I think I spent around 10 days on Raman and more than 2 months on IR. It's not favorable for modeling, I think, at all, and quite challenging, starting from data preparation and collection. It took almost a day to collect all the IR data we need, and the processing also takes a lot, but I've learned a lot from this, and I'm happy to share what I've learned so far from IR. If any of you are interested or might want to use IR in your analysis and work. And so again, we have the same data set, which is 48 mixtures of 6 different amino acids with random ratios in each sample. And the goal is to use the spectral data to predict these each compound ratio in the mixture. So it's a complex idea to predict ratios from a mixture, because all the peaks overlap, and it's the power of models that learn this sort of things. So here we took 4 replicas of each, and inside the instrument itself, which we use this instrument from some shared facility instrument thing at in chemistry department. We use Fourier transform infrared spectroscopy with attenuated total reflectance, and it has a blank, which is that attenuated total reflectance crystal, something like diamond. And when we remove this blank, everything we are collecting is a background or background free, and it's just the Raman spectra of the sample to use. So we could take just 4 replicas of each spectra, and internally it averages over 8 spectra. So we can roughly say from each measurement, we've collected 32 different IR spectra. Again, it's the correlation map. So when you collect from this instrument, when you collect IR spectra, is 3,351 features, because it's a very extended range from near IR to mid IR. And I've just run a dimensionality reduction and it reduced to 844. This is the correlation map. But here you can see the just original analysis on the data before any augmentation or any further analysis. So after the pre-processing, which is just normalization and averaging here. So you can see that for some compounds like aspartic acid, which is not that IR active, and the results is not good. And the whole effort here was to make the prediction good on such compounds that doesn't originally have a good Raman activity. The same for CNN, and in this case, for example, PLSR, since the number of data after averaging is not high, PLSR is still better than CNN. So as you know, models started performing as long as you improve the number of data, increase the number of data. So the challenge was high number of features for IR, and there are a couple of solutions introduced, like dimensionality reduction using DWT. So because I want to use the same thing that I've learned, I change this Raman percent transmission for each Raman spectra to absorbance. If you do so and reverse the wave number, you can get the exactly same thing from IR. And they are identical if you do these simple changes, make these simple changes. So I first make Raman as IR as Raman, and then I applied dimensionality reduction using discrete wavelet transform. And the results still wasn't that good. And then I keep the near IR region, which is 2000 to 4000. It's still a lot of features. And then I further use just a shorter range with 1300 features. And I further reduce the dimensionality here to 344, and eventually I've received the best result just from trial and error from this section. But also I've read that so here is an IR spectra that I'm talking about, and the IR spectra has percent transmission as a transience as the y-axis and wave number as the x-axis. So here I just plotted based on the number of pixels, but if you plotted based on the actual wave number, it's reverse. It means it starts from higher numbers. To make it a Raman, I just reverse the wave number and also change the percent transmission to absorbance, and then applied all the analysis I need. But you can see that here in near IR, you have lower, as you go toward mid IR, it's noisier, but for modeling purposes, this region in mid IR provide a better result than this region. That's why I cut these two regions separately and done the analysis separately to see which one provides a better improvement. So here is just from dimensionality reduction on the whole IR spectra from 3300 to 844. I think it's increased a little bit. And then, yeah, I should have this slide earlier. I was talking about these two regions, near IR and mid IR, that I've received better results for just cutting the spectra and keeping the mid IR and do all the analysis on those noisy like region. This is from 2000 to 4000. Here, 2000 to 4000. And here's the results. If you compare, it doesn't improve, but it degrades. And then I pick this region from 650 to 2000. But I further, again, it improves significantly, but I further decrease the number of features to eventually 274. And the results starts get better. But I think these are not publishable results or something, but I wasn't satisfied with these two predictions. And I put effort on improving the prediction of all the models, specifically for these two. And when you came across such problem in analysis, one solution is data augmentation. And data augmentation means you generate some statistic data as you have, similar, the main features should be the same, but you introduce some noise. For example, if an image, you can rotate that or add a little bit of noise. This sort of things here to generate synthetic Raman spectra. This is the eventual best results that I get from leave one out cross validation. But I've tried many different things, but the logic behind all these 5 different methods is to get pure Raman spectra and with a random coefficient or random weights and make a linear combination of these pure Raman spectra to generate a Raman spectra that is similar to what you have done in the experiment. So you can do whatever you have done in the experiment, exactly the same thing, and synthesize more Raman spectra, or you can use different weights to just add to your number of samples and make it favorable for modeling purposes. To summarize, I keep this region from 650 to 7080, and then on top of that, I apply the dimensionality reduction to shrink down the number of features using this formula for to make the transmittance to absorbance and make it exactly identical to Raman. And then for the data augmentation, these are different methods that I applied, and the best results came from synthesized mixtures. And so at this point, you need to make sure that your augmentation is efficient. To verify that, you need to keep a part of your actual experimental data aside as tested and verify your modeling on actual tested from the experiment to see what we have done, or the synthetic data that you have generated gives you this, you're learning the things that it should learn, and you can verify that by test it on the experimental actual data. And to do that, I assess using PCA tests to see how the distribution of test and train is. And eventually, I ended up with not working this synthetic mixtures thing that it's working pretty much well for IR if you want to augment for IR, but not the same for, it's working for Raman, excuse me, but not for IR. And eventually we are just looking for why this augmentation wasn't successful. So this is the distribution. This is the raw IR train and tested. And this is the augmented IR. And this is everything all together. But just by plotting them, you cannot assess whether they are a good representative of actual mixtures or not. So I've done the PCA test, and PCA test shows that, so if you shrink the principal components to 2 principal components, then you have a 2D representative of your data. And if you label the data to test and train and plot them out here, you can see if they have the same distribution or not, because obviously if you have a train distribution here, you couldn't expect those to learn somewhere from here. Like these dots, blue and red was completely separate, but they are well distributed. So I've used, so since I first implemented the synthetic model, and then you easily can ask to generate as much as synthetic data you wanted. And obviously, as we increase the synthetic data, the model starts outperforming, get better and better. But here is a challenge: when you apply the same model on a test set, it's not successful on predicting the actual experimental data. These are from two different combinations, this is a pure random combination. It means I took pure spectra and randomly just weighted each pure spectra. It's a linear combination of pure spectra. And here is the average mixture, which is another method to synthesize data. And again, it's not successful. Here's the same, it's another thing. But interestingly, we just pursue these to see if we can get an easy solution around these, to just by tuning or changing parameters in the models to get things more realistically, to give us a good results on the test set, which means a success to me. But yeah, on this part of analysis, Natalia also helped me a little bit to figuring out what's happening. So when I plotted this correlation map, you can see that the synthetic is quite random and there isn't any specific. For example, for this sample 37, it has a good correlation with all the other samples, but everything is random in synthetic. Yeah, and Natalia also further did a little bit of analysis. I'll just quickly go through it, but it might be interested to you why it's not working. So when you take all this pure Raman spectra and you just pinch everything in the tail of the spectra to be zero, all the spectra sit above zero, like there is nothing under zero. But the thing is happening is that when I just make a linear random combination of pure spectra, I generate these blue mixture spectra, and this is an obvious thing because all the pure spectra are above zero, and any combination of them also is above zero. But for the experimental mixtures, when you pinch everything here in the tail on the zero, a part of it come under zero, and this is not something that we can easily simulate because we still don't know what's the reason of this behavior is, but we know that lots of experimental factors can affect this behavior. So Natalia did this part of the work that she tries to calculate the Raman activity of each pure spectra. And so for these making these mixtures, you have this weight that randomly you took, but on top of it, each pure spectra has a different Raman activity. Some of them are more Raman active, some of them, especially the ones that has the poorest prediction, has low Raman activity. She calculated the Raman activity using a least square model. Here there is no ambiguity because the number of features and the number of features and inputs are the same, so you can easily calculate this coefficients. Still, when we apply and consider those coefficients, nothing in synthesis come under zero. Everything, even though it's not like this, just two separate data sets, but it shrinks things down and bring it to these red experimental region, still nothing under zero. It means in the synthesis, considering IR coefficients and activity, you cannot simulate something that represents the changes and behavior that are happening here. So this plot shows that absolute intensity of Raman spectra depends on the compound and several experimental factors, and it's not an absolute because it's changing when you make a mixtures. Here we don't have that point, but it shows that there is no absolute minima, and this absolute minima is changing in experimental mixtures. And that's why we cannot generalize a method on them. The absolute minima is changing. And
Also, can I ask a question? Just as far as this, the background, it just kind of looks like kind of like the way you would treat maybe a fluorescent background and non-regular background. So is when you see the differences between like you see like you set the tail point to be 0, but then in the middle is below 0. So like, are you not doing background correction on this, or is this just what the background correction spit out? Or and I guess yeah, like what should I take from this?
okay, the thing you should take from this, first of all, is that when you let us go normalize the spectra and define a 0, an absolute 0. For the experimental data, you have some regions that are under 0 before you normalize that, or even though you normalize, things are under 0. But for the synthetic spectra, everything, any kind of combination, even considering the coefficients, everything is above 0. So you cannot ever, never make a combination of synthetic spectra that represent this region that is under 0. And also for the background subtraction, I've done that to just remove the background and make sure that there is no effect. I did the same with background removal, but the results haven't improved, but degrade by 1 or 2% for the actual experimental data.
That's interesting. And can I also ask too, like, would you consider doing a second derivative and then mean centering it, and so with the background would maybe stay more constant?
Take the second derivative and mean center, and then try to synthesize data on that form of IR.
I guess that would be like your working data set.
No, I haven't tried the second derivative. But yeah, we just here try to understand why synthetic spectra, considering even the coefficient, is not working quite well. And here just shows that for all the pure compounds, when you d-score normalize them and bring the tail to be 0, or in other words, remove a background, the local minima changes, and it's not absolutely cannot do mean max normalization because the mean is not absolute and it's changing. And here is an eventual analysis. So if we have these 6 different pattern of pure spectra, the experimental mixtures is the red, and the individual field scaling, it means to calculate for each mixture, calculate the IR activity individually, but it's not a generalized method. You should just calculate, because each compound should have a fixed Raman IR activity. So even though this one, this longer dash gives better results, but this is a more generalized version to just calculate the Raman activity of each pure compound separately, and it's a generalized thing, and apply that for all the mixtures, not individual calculated. And this is the no scaling, means not considering IR coefficient. And here in this difference, it shows the difference between each of these 3 with the experimental mixtures, that the individual one has the lowest difference, and the simultaneous fitted the next, but the difference is not huge, and the no scaling obviously was the worst. More examples of it. So I had this data on my hand, and I was so excited to give it a try. So just for fun, these 3 slides shows that how in different mixtures as this compound contribution decrease, how on the spectra you can see it start vanishing. Anyway, so I did a try to these data. When I plotted them, they looks like quite the same. This is the actual, and this is the augmented one for test and train. But I don't know, maybe there is a deficiency, like something wrong happened here. I haven't received a good results on that. So here we plan to pursue this more, but also we decided to, no, it hasn't finished yet. So here, this slide might change because it might be a problem with the way I read Natalia's data, or the errors might happen, but we expect that after considering IR activities, the results improve to just non-scale combination of pure IR spectra, because here we showed that it's the difference between experimental actual IR data decrease in such a method by considering IR activity. And I further generated more plots. It's mostly related to analysis part, like we can forget about IR at this point, but I did a comparison plot between R squared or any other metrics that is suitable for regression purposes, like R squared or mean square error, versus the number of samples. And also I've generated another plot that shows R squared versus the number of replicates. To do this sort of analysis, it takes a long time, because you should, when you want to consider different number of replicates or different number of samples, it takes a long time because there are a couple of for loops, and for each training, for each for loop and each step, it should does all the training, collect the metrics, and go to the next one. So I haven't calculated how many times it goes through that for loop, but it takes quite a meaningful amount of time. But the result is like this. Obviously, as the number of replicas increase, the prediction results for both actual IR and Raman increase. But this is significant that when we use just here 32 versus 90 spectra for Raman, there is a significant difference between the prediction. So it means it's better for us. It's an optimum point that what's the number of replicates that give us the best results versus the infinite number of replicates. And also for the number of samples, this is also has done both for CNN and PLSR and Raman and IR. I think since it took a long time, I might not have done this for CNN model, but these results are for PLSR. And as the number of samples increase, the model performance is also increasing. Yeah, here in this plot, you can see in the comparison, I think this plot is taking a lot of a significant amount of time to be completed and generate these. And I'm happy that I've implemented and work on those codes. And I'm hopeful that I can use in other part of my project. Yeah, and this is that interesting thing that I was talking about. So if you are really interested to just use IR data and also apply some deep learning models, and you're not happy with 1D IR or Raman, you can apply first a continuous wavelet transform, and then a scale map on the data and generate an image of that spectrum. So it's a 1D IR spectra, and this is the same thing, the same features, but if you apply a continuous wavelet transform and then apply a scalar map, you can get a image of the same thing, and then it's ready for different modeling purposes. I think it was a cool thing that I've learned, and I quickly just implemented. It was interesting, but I haven't pursued this because it wasn't part of my objective. So to wrap things up is that, so I've done a million different analysis and I've learned a lot from this. I'm happy from that aspect. And I see the benefits of all these learnings in my other projects or pursuing these or new ideas. But what I eventually want to put in the paper that I'm really, I'm so motivated to bring this to a result, because you're happy when you get a result from your hard work and effort, is that I want to talk about IR just itself, all the processing and modeling steps, but I want to add some complexity to it by doing a little bit more analysis using more fluorescence and noisy spectra. And from the heterogeneity and homogeneity effect, I want to add to my mixtures, amino acid mixtures, some coarser minerals that has a different size distribution versus my powder mixtures of amino acids, and see how it affects from the modeling perspective and results. And also it's really interesting for mineralogists and soil science, because when you combine amino acids, for example, and minerals, it's an environment like mineral soils or carbon soils. It's interesting to be done specifically from the analysis point of view, because they are not normally applying modeling stuff, and they are still, some of them still just using fitting or hand analysis and comparing these. So from that aspect, I might pursue this work and end this with the things that I've explained. But for the IR, it would be really interesting to figure out what is happening there and even test the difference. At this point, I'm a little bit tired on working on IR, but we have this in plan to continue that as a separate thing and just do separately. So separate the IR and Raman from each other. And the other thing was to fuse IR and Raman. So for that, also I've done some literature review. One was so exaggerating that the IR itself was low prediction results, the Raman was low, and when they fused these two, everything increased by about 10%, which was questioning when everything is going so perfectly like that. But I haven't give that a try because it wasn't clear to me what the goal here, to use IR to use a Raman performance, which was almost perfect, to increase the performance of IR, which was low. So it wasn't an equal comparison. So I haven't pursued that, but that's another idea that came across, and yeah, talked and discussed that. Okay. I'm glad to take any questions.
Good. Great. So I have, let me make some observations here. And first of all, I think that everybody should have a pretty good idea now that you've got the experience that if anybody's got a multivariate analysis question, they should come to you because you've tried so many things and tested everything so thoroughly. I think I've got, we should sit down together and talk about your IR problem. You know, I've got some suggestions. I think I can help you make a lot more. Those data should be giving you much better classification accuracy than you're seeing. And I mean, there's a few clues here, and I'll just say them now, but I think that what we need to do is sit down and have a conversation together, just you and I. Excuse me. I've finished all of my water, so I've got a little bit dry throat. But so you mentioned both absorbance and transmission back and forth, and you know there's a very important difference between those two. Transmission measures the intensity of the light that's collected by the detector divided by the intensity of the light that you start with. And that's a ratio. Absorbance is the derivative of the intensity as a function of the distance, or the integrated derivative of the intensity as a function of the distance. And they're related to each other in a logarithmic relation. And so you have to be careful about mixing up those data types. The other thing is that neither one of them can ever be negative. The only way you could have a negative transmission is if you had a laser. You know, if you had gain in your medium and the intensity of the transmitted light was greater than the incident light. So I mean, I think that there's some tricks we can talk about that you can do with your data, I think. And Matt was, I think, hinting at a couple of things that would be good. And we'll talk about that. So I think that there's a lot, you've collected an enormous amount of valuable data. And I think there's a lot of things you can do to it to make it meaningful. In particular, I guess I'll say one more thing. The information either in Raman or IR, it's almost impossible to take the information out of one spectrum as an absolute intensity and relate that to any other spectrum, because so many things affect the absolute intensity that you measure. And what really matters is the relative intensities. And so that means you have to be really careful about what you're balancing against what. I mean, so if you cut off part of the spectrum and you might take away a really tall peak, and that makes all of your other peaks have a relative intensity that's much higher. And so, deciding where you cut, for example, could really have a big effect on the shape of the spectrum and what happens in your multivariate analysis. So we'll talk about those details, and I'll find out a little bit more about the strategies that you used. But I think that, normalizing and mean centering and second derivative, those are all things that will uniformize your information such that one spectrum will be very consistent with another one, with another one, and with another one. And so that the only differences that your informatics looks at are the significant differences because of different structures. Yeah, I think we can really get a lot more information out of this data set. There's no reason why your IR should not be as good, if not better, than your Raman at the kind of classification that you're doing.
Thanks, Ed. Yes, but here I'm doing a quantitative analysis that I want to exactly predict the ratios of pure amino acids in X mixtures. And so one problem that I see IR has is this high number of features that gives me not a satisfying results at the beginning, and I tried different methods like dimensionality reduction or cut the IR and separate the mid IR from near IR to get better results. So for the boundary, I haven't a good justification why exactly at this point, but I know that mid IR in the analysis normally provide a better result than.
Yeah, I worry a little bit about that because of this business of the normalization. The other thing is that yeah, you're right. If absolute, so it's not so much that absolute intensities matter, but I mean, just imagine that you had a common ingredient in all of these samples. Let's say every sample had exactly the same amount of something like diamond in it, so that you could measure every peak's ratio to diamond. And on certain days, you'd see the diamond with a more intense peak and a less intense peak, but that would be your primary standard. Here, you're allowing all of the intensities to vary. That still should be okay. They're relative. The relative measures should ultimately relate to the composition of the sample. It works in Raman, so it should work in IR. But I think there's some subtleties in the way that you map the data over. And you're right, it might be related to the very large number of features.
Yeah, yeah, I'm glad to have this session of discussion.
Yeah, I'll suggest one or two things that are really going to be simple to try. And you can see if they make a huge improvement right away, then that's great. I'm glad. If they don't work, well, then we'll have to sit down and think about why fundamentally there's a problem. But it's a very, very impressive collection of samples. And I think that it's a good place to really prove some fundamental things about spectroscopic classification. I think it's going to be good.
Thank you.
So a question I had also, this is one I wrote down right at the beginning. So a typical protein, I don't know. So there's 21 amino acids in living materials, naturally occurring amino acids. And are there proteins that contain a sufficiently small fraction of those amino acids that one could imagine asking this question? If you took a mixture of amino acids that was exactly equal to the stoichiometry of a protein, how different would the spectrum be of the mixture compared to the pure protein?
You mean if the protein has exactly these 6 amino acids, how different the actual protein spectra is going to be from synthetic mixtures?
Yeah. So the only difference, I guess, if you have the fractional numbers of proteins exactly right, the only difference can be the difference that's caused by the bonding. And I guess that's going to change every N group, though, isn't it? That's going to make a big difference. I take my question back, because every protein is going to have an extra bond that comes from the fact that it's hooked to the other ones. And so that's going to, that will show up definitely in the IR spectrum. Yeah. Okay, well, Mahsa, can we talk tomorrow? I'll come into the lab tomorrow and we can talk.
Tomorrow, I think maybe Friday, because I'm quite busy with that experiment of laser shift for Termera.
Okay.
How about Friday?
Okay. Yeah, that'll be good. But I'm going to be in tomorrow anyway, if anybody else, just for everybody else's knowledge. Yeah, again, my apologies for not being there today.
No worries. Yeah, thank you all.
Okay.
I have one general question, like how much, like if you take 1 gram of soil from whatever soil samples you have here in the, how much percentage do you expect to be amino acids?
So the importance of amino acid is that it's categorized in the carbonation part of the soil, and the carbon of the soil is of quite great interest, because due to carbon sequestration stuff, it's really important to recognize the amount of carbon and further categorize and classify the carbon content of the soil.
But how much?
Yeah. I think, I don't have an exact number, but it should be a too little number, like shouldn't be a high percentage. But yeah, the reason I picked the amino acids is that it might have some other, I haven't explored writing an introduction about amino acid itself, but the main purpose of me was to have a grand play database to work with, and it was just easy and straightforward. I picked this, but also it's of significant interest because of soil, and we have next plans to start adding up things onto that, like minerals and other stuff. And these minerals are natural minerals that Natalia has ordered from a state. They are real stone that's coming from nature, and they are much more pure than some of the samples that we ordered. They are very precise and pure.
And then you were talking about like mixed samples, and then you write something like synthesized amino acids. And I was wondering, is it like you synthesize the amino acids separately and then you mix it mechanically? Or do you have some samples which you synthesize and then you have peptides?
No, so mixture or mix means using pure spectra, commercial pure amino acids, nothing experimental here, and just mix them together physically or mechanically by hand. And when I was talking about synthetic and synthesized thing, it means doing the exact same thing, but in the model and not going to lab and do these things manually.
Okay, so mixtures means you really do it in the lab, and synthesize means just a model where
Yeah.
you just have you play with the data.
Yeah.
Do you just then add the two spectra together? Or what do you, how do you synthesize? Is that what you mean? Or am I completely?
Synthesize.
Yeah, do you,
But synthesize-
you take two spectra, like you take aniline, I can't even name it.
I either, it's
You
aniline
take two
part.
of them and you like just add the two spectra together.
No, it's a linear combination of them. There is a weight associated to each compound. And this is random because these weights are something that is random also in the experiment. It's our Y matrix or Y label, which is the weight of each amino acid. So aniline is, so we normalize these weights to sum up to 1. For example, aniline is 0.1, 0.2, 0.3, 0.1 again, like this.
And where do you get the weights from? Do you do it in the molecular way?
No, it's the weight ratios.
Like weight percentage.
Weight
or mass.
Yeah, weight.
Oh.
Yeah.
And we pick the random combination because from the design of experiments point of view, for if you want to do mixtures of dried compounds, if you just randomly combine them, is the most efficient way. So we shouldn't explore any other design of experiment method.
But for just as an example, so I do understand how that works, that if you had like, say, a 1-to-1 ratio, would that be the same as just taking the two spectrum?
Yeah, but we normalize things to be 1. Yeah, 0.5, 0.5, and the rest of it to be 0. It means 0.5 of 1 and 0.5 on the other end, something like that. Yeah, it was the first.
It's just like.
Yeah, it was the first step, but the second step is considering the IR activity of each. So in that case, it's not a 1-by-1 combination, but depending on how active each are, it might increase and decrease for each of them.
I have another question. So you said that you're transferring IR data to Raman data, but how do you account the effect that IR is like change of physical units, and like Raman is like the change of fluidity? How do you change the IR spectrum? Like
So-
the physics behind it.
Yeah, as far as like, I know that both have, so the intensities or the peaks we get here is the transition of the vibrational mode and rotational mode of these two samples. But as you mentioned, dipole moment and versus polarizability, it depends on its symmetric polarization or asymmetric polarization of the sample. They categorize as ro-vibrational spectroscopy, and because they are based on the transmission, vibrational transmission, that's why I consider these to have the same nature, because it's classified as the same group.
I think also you have, say, Raman and IR activity sample. So we both relate to when you see the wavelength, the wave numbers of Raman spectra, which is the same, you take an IR spectra, that same sample, go, I think in should be able to get to, I think that's what I was.
I think we did like compliment not same, in terms of their number range, yeah, it's going to the same range of in terms of this.
I was gonna ask too, does rate number really make sense? What is your x-axis? It should be.
So here actually,
How do you have a relative rate number when the rate
so for the original IR, it's percent transmission and also wave number. Because the wave number is the energy of the vibrational transition. And this is how you define that.
So, yeah, right, but usually if you see 0, you're talking about relative rate number, right?
Yeah, here I've just plotted, so it's not correct. I've just plotted by the number of pixels.
Yeah, that's.
So sometimes it might be confusing for some plots, but since a point, I just use the same template each time you get. But some of them, when you see 0, it's not based on the number of pixels or number of points. But sometimes you see the region, but not starting from 0. It's the wave number. It's just the frequency energy.
And I have one last question. So I think what I could extract from the talk is that like Raman worked very well with your data and started IR. So is that okay?
This is what I witnessed, but yeah, this is the thing that I witnessed. So it's not exactly
question. Then, like, if Raman is like data are so similar, why is there such a big difference?
So I think there are a couple of differences here. First of all, is the number of samples. Obviously, Raman number of samples was way higher than the other one, the IR. But I tried to make an apple to apple comparison when I showed these plots. These nearly use the same number of compounds, but still for IR it averages over 8. So I actually didn't have 32 different spectra, which its own noise associated node. It was actually 4 spectra, but internally each average over 8. So this is the first difference, and the second is the number of features, which was 3 times more than Raman.
I have a question right there. Why do you think higher number of features lead to like poor performance?
Yeah, I think at this point, if I've collected, for example, 1,000 actual IR spectra, and considering those 3,000 features, I might see a better performance and I could better compare. But it honestly, in terms of manual work, it's impossible to prepare and collect all those data with IR.
Why is it so complicated?
It's taking so long. So each measurement, you started around being 8, 9 a.m. and it's done by 3 p.m.
Oh my gosh. It's like IR is pretty fast. But when I've done it, it's like depending on how many.
It was 48 multiplied by 4 and multiplied by 8 because it's average internally. So if I was about to do the same thing with a Raman, it took me 45 minutes.
Yeah, I
Maybe later
think
then.
So data analysis in Ghana it's not really straightforward. People who publish their work. You can get it as a model and maybe you run it from look at your model, describe what it is. So you go with the advisor and say what Mark said. And then also I have another example for maybe looking into different types of communications. That one is terrible, but the other
Yeah, but I think even though it cannot be generalized that like everyone is working with IR or Raman using the same model, but the thing that can be generalized is to, if you really want to get a good prediction result, you should make your strengthen yourself with some good, powerful machine learning models. They definitely provide a good result without the requirement for pre-processing and either dimensionality reduction, which method is working the best, or for example, in our other project, we are mostly involved with stairs method to take the difference or reconstruction. So as long as you learn how to build these models strongly and collect sufficient number of data, and at this point, definitely Raman is much better than IR if you have a problem like this. Obviously, different problems have its own instruments and solutions, but it's the same thing. Just go with Raman and also build a good prediction model and collect sufficient number of data for that. I think this one can be generalized.
I can send you an article that one of our co-professors they have there's a group that only did data. They have that in packages. So
Yeah, that was from where?
He's called performance cache. I don't know if I can send you.
Yeah, sure. Yeah, and I think it's quite novel in Raman, even though deep learning or machine learning methods is so common, everyone is now hearing about that, but when it comes to literature or when it comes to actual works, it's still a place to make a lot of progress and a lot of work, because I barely could find a few works that just implemented actual models to see how it works, and definitely it requires a huge number of data, which is another challenge. But still, it's a place to grow, and I would be interested to work more in this area.
Okay, just one thing. I was familiar with the work you've done before, so we didn't ask anything, but for the data fusion part, if you're asking why we're doing the data fusion and why we're like making a combination between like Raman and IR, I think you have to work with the IR data. It's worth working on it, and you can get a lot of good things about it. So you can get some features from your IR data set and then combine it with the Raman, and it will increase the rate of your decision making in your PLS model later. So it has a lot of benefits if you go through that way. But first of all, you have to figure out what to do with the IR. And also, I think, yeah, it is too soon to just drop the IR because you have a lot of things to do on it. And I have some suggestions.
Yeah, and that's why it was last week. I almost cried because I've done a lot and I really wanted to push it toward an end, but it still needs to be improved and more things need to be done. And I hope that I can just do this job by the end of the year and just Raman and do more analysis or comparison on IR separately.
That means you have ideas.
Yeah. Okay, thanks
Good.
everyone. Yeah.
All right, Mahsa, I'm going to have some good suggestions for you. We'll meet on Friday.
Yeah, sure. Thank you, everyone. It's been a very long meeting. Thanks for patiently staying with me. See you soon.